April 26, 1962. The Nevada desert trembled as titanium skin absorbed the first photons of dawn at Groom Lake. Test pilot Louis Schock checked his pressure suit one final time, aware that the classified aircraft waiting on the tarmac represented a technological leap so profound that even mentioning its existence could trigger an international crisis. The A-12 Oxcart stood motionless under armed guard, its chines and delta wings designed not merely to cut through atmosphere but to render Soviet air defense doctrine obsolete. Schock knew the stakes. If this prototype failed to achieve Mach 3 sustained cruise at 90,000 feet, the United States would remain blind over denied Soviet territory. If it succeeded, America would possess an aircraft that could photograph missile installations, submarine pens, and nuclear test sites before radar operators in Moscow even understood a penetration had occurred. The engine start sequence began. Two Pratt & Whitney J-58 turbojets ignited with a sound that resembled controlled detonation. Schock released brakes. The A-12 accelerated down the runway at a rate that defied conventional thrust-to-weight ratios, rotated at precisely the calculated airspeed, and climbed toward an altitude where the sky turned indigo and the curvature of Earth became visible. Soviet intelligence analysts monitoring American aerospace developments had no idea that their largest titanium supplier had just provided the metal required to build the weapon system designed to humiliate them. The arrogance in Moscow was absolute. Soviet Premier Nikita Khrushchev had publicly declared after the downing of Francis Gary Powers and his U-2 on May 1, 1960, that no American reconnaissance aircraft would ever again violate Soviet airspace with impunity. The SA-2 guideline surface-to-air missile system had proven its lethality. Soviet propaganda organs broadcast the technical specifications of the triumphant interception. Altitude of engagement 70,000 feet, missile speed Mach 3.5, proximity fuse detonation within lethal radius. Khrushchev displayed fragments of Powers' aircraft in Gorky Park as proof that American technological superiority was a myth. Soviet air defense commanders received commendations and promotions. Strategic Rocket Forces officers assured the Politburo that the integration of P-12 Spoon Rest Early Warning Radar, P-14 Tall King Acquisition Radar, and Fan Song Guidance Radar created an impenetrable defensive network. Marshal of the Soviet Union Rodion Malinovsky told the Central Committee in a classified briefing, declassified decades later, that any aircraft attempting penetration above 50,000 feet would be detected at ranges exceeding 100 miles and engaged with multiple missiles before reaching high-value targets. The Fan Song radar system, Malinovsky explained, could track targets with a radar cross-section as small as 5 square meters with sufficient precision to guide SA-2 missiles to within 300 meters of the target. Soviet confidence extended beyond surface-to-air missiles. The Mikoyan-Gurevich Design Bureau had developed the MiG-25 Foxbed interceptor specifically to counter high-altitude American reconnaissance platforms. With a maximum speed of Mach 2.83 and a service ceiling of 75,000 feet, the MiG-25 was designed to climb rapidly, execute a zoom intercept profile, and fire R-40 air-to-air missiles at targets above 60,000 feet. Soviet test pilots reported successful intercepts against drone targets simulating U-2 flight profiles. The USSR believed it had closed the altitude sanctuary. Soviet military journals published assessments stating that advances in ramjet propulsion and high-energy fuels had reached theoretical limits, that no manned aircraft could sustain speeds above Mach 2.5 without catastrophic structural failure, and that metallurgical constraints made sustained Mach 3 flight an engineering fantasy. The Americans, Soviet analysts concluded, would be forced to rely on satellite reconnaissance, which offered poor resolution and inflexible orbital mechanics, or accept the prohibition of manned overflights. Either outcome represented strategic victory for the USSR. Yet the Central Intelligence Agency and a small cadre of Lockheed engineers working under the leadership of Clarence Kelly Johnson knew that Soviet assumptions rested on a fundamental miscalculation. In August 1959, the CIA awarded Lockheed's Advanced Development Projects Division, known as Skunk Works, a contract to develop an aircraft capable of sustained Mach 3.2 cruise at 90,000 feet with a radar cross-section low enough to delay detection and reduce engagement probability. The program received the codename Oxcart. Johnson's design team understood that achieving these performance parameters required abandoning every conventional airframe material and propulsion concept. Aluminum, the standard material for subsonic and low supersonic aircraft, would melt at the skin temperatures generated by Mach 3 flight. Stainless steel offered thermal resistance but imposed unacceptable weight penalties. The only viable solution was titanium alloy, specifically beta 120 titanium, which could maintain structural integrity at temperatures exceeding 600 degrees Fahrenheit while weighing half as much as steel. Titanium presented extraordinary fabrication challenges. The metal was so reactive that exposure to chlorine, cadmium, or even certain inks caused embrittlement and stress fractures. Lockheed engineers discovered that titanium panels spot-welded during summer months failed within weeks, while identical panels welded in winter remained intact. Investigation revealed that Burbank's municipal water supply was heavily chlorinated in summer to prevent algae growth. The solution required switching to distilled water for all titanium cleaning operations. Tool bits shattered when drilling titanium. Lockheed developed specialized carbide drill bits that could make 100 holes before requiring resharpening. Cadmium-plated wrenches left residue that weakened bolt heads under thermal stress. Every tool in the Skunk Works facility had to be inspected and replaced. The greatest challenge was acquiring sufficient quantities of high-grade titanium. The Soviet Union controlled the world's largest reserves of rutile ore, the mineral source of titanium. Lockheed required over 100,000 pounds of titanium for the Oxcart program. The CIA established a network of shell corporations operating through third countries to purchase Soviet titanium without revealing its intended use. Invoices described the material as destined for pizza ovens, commercial aircraft components, and industrial furnaces. Soviet export authorities approved the transactions. The metal that would form the airframe of America's most advanced reconnaissance aircraft was shipped from Siberian mines to California via circuitous routes designed to obscure origin and destination. Propulsion requirements were equally severe. No existing turbojet engine could sustain Mach 3 cruise for the mission durations required by CIA operational planners. Pratt & Whitney developed the J-58 engine, designated JT-11D20 in company nomenclature, specifically for the Oxcart program. The J-58 incorporated an innovative air bleed bypass system that bled high-pressure air from the compressor section, routed it around the combustion chamber and turbine, and injected it directly into the afterburner. At speeds above Mach 2.4, this bypass system functioned as a ramjet, with the afterburner acting as a ramjet combustion chamber. The engine transitioned from pure turbojet operation at lower speeds to a hybrid turbojet-ramjet configuration at maximum velocity. This allowed the J-58 to produce over 34,000 pounds of thrust in full afterburner while operating continuously at temperatures and pressures that would destroy conventional engines within minutes. The engine required a specialized fuel. Standard JP-4 jet fuel was too volatile for the extreme thermal environment of Mach 3 flight. The fuel system of the A-12 used JP-7, a low-volatility turbine fuel developed by Pratt & Whitney chemist Clarence Brown Eichmann in 1955. JP-7 had a flash point of 140 degrees Fahrenheit, compared to 110 degrees for JP-4, and exceptional thermal stability that prevented breakdown and coke deposition in fuel lines subjected to temperatures exceeding 300 degrees Fahrenheit. The fuel also served as hydraulic fluid for engine control systems and as a heat sink for avionics cooling. JP-7's composition included hydrocarbons, fluorocarbons for lubrication, oxidizing agents for combustion efficiency, and a cesium-based additive designated A-50 that ionized the exhaust plume to reduce radar and infrared signatures. An A-12 consumed between 36,000 and 44,000 pounds of JP-7 per hour at maximum cruise, requiring aerial refueling from specially modified KC-135Q tankers carrying compatible fuel. The ignition system for JP-7 required trithylborine, a chemical compound that ignites spontaneously on contact with air, because conventional jet fuel igniters could not reliably light the low-volatility fuel at high altitude. The airframe configuration incorporated stealth characteristics years before the term entered common usage. Kelly Johnson and his aerodynamics team understood that radar cross-section could be reduced through shaping and materials even if true invisibility remained impossible. The A-12 featured chines that ran the length of the fuselage, creating wedge-shaped leading edges with shallow angles that reflected radar energy away from the transmitter rather than back toward the receiver. These chines also generated vortex lift at high angles of attack, improving low-speed handling during takeoff and landing. The leading edges of the wings and chines were filled with a composite material consisting of iron ferrite and asbestos fibers that absorbed radar energy rather than reflecting it. The vertical stabilizers were canted inward to reduce side aspect radar returns. The overall design resulted in a radar cross-section estimated at 5 to 10 square meters from most aspect angles, significantly smaller than the 30 to 40 square meters of a U-2. This reduction in radar signature translated directly to reduced detection range. A P-12 spoon rest radar with a nominal detection range of 100 miles against a conventional aircraft would detect an A-12 at approximately 60 to 70 miles, giving Soviet air defense crews far less time to execute intercept procedures. The A-12 measured 102.6 feet in length with a wingspan of 55.6 feet and a wing area of 1,795 square feet. Empty weight was approximately 60,000 pounds. Maximum takeoff weight reached 120,000 pounds fully fueled. The aircraft was painted a dark blue color, almost black, that engineers discovered dissipated heat more effectively than bare titanium. This paint scheme became iconic in later reconnaissance variants. The single-seat cockpit placed the pilot in a pressurized environment with minimal forward visibility due to the long nose section housing cameras and sensors. A periscope system allowed the pilot to observe the rear quarter during high-speed cruise when looking over the shoulder was impossible due to helmet restrictions and spinal stress. Flight testing revealed performance that exceeded even optimistic projections. On May 4, 1962, during the 8th test flight, pilot Louis Schock pushed Article 121, the first A-12 prototype, to Mach 1.1 at 40,000 feet. Subsequent flights progressively expanded the envelope. By January 1963, A-12 aircraft had reached Mach 3 and 78,000 feet. The full design specification called for Mach 3.2 at 90,000 feet, and testing proved the aircraft could meet and exceed this requirement. Pilot Jack Weeks achieved Mach 3.29 at 85,000 feet on an operational training sortie in 1967, making the A-12 officially the fastest manned aircraft in sustained-level flight. The SR-71, developed from the A-12 for Air Force use, was slightly slower with a maximum speed of Mach 3.2 due to increased weight from the second cruise station and additional sensors. At maximum cruise, the A-12 covered 1 mile every 1.8 seconds. The aircraft could traverse the entire continental United States from coast to coast in approximately 70 minutes. At 90,000 feet, the pilot could see the curvature of Earth and observe weather systems stretching across hundreds of miles. Cabin pressurization maintained an equivalent altitude of 28,000 feet, requiring the pilot to wear a full-pressure suit identical to those used by astronauts. Skin temperatures on the nose section reached 800 degrees Fahrenheit during sustained Mach 3 cruise. The titanium airframe expanded by approximately 11 inches in length due to thermal expansion. Fuel tanks leaked on the ground because they were not sealed. The design relied on thermal expansion during flight to close gaps and seal the tanks. Ground crews routinely observed fuel dripping from the aircraft before takeoff. This was considered normal operating procedure. The turning radius at maximum speed exceeded 86 miles, requiring vast expanses of restricted airspace for test operations. Area 51, the classified test facility at Groom Lake, Nevada, provided the necessary security and spatial requirements. By 1965, after thousands of test flight hours accumulated by CIA pilots and Lockheed test pilots at extraordinary personal risk, the A-12 was declared operationally ready. The aircraft met all design specifications. Sustained Mach 3.2 cruise, 90,000-foot altitude, 2,500-mile unrefueled range, and a sensor payload capacity of 2,500 pounds for cameras and electronic intelligence equipment. Soviet intelligence services remained unaware of the A-12's existence for years after the program began. The extreme security measures surrounding Oxcart prevented penetration by human intelligence assets. The test facility at Groom Lake was chosen specifically because it was located in a remote desert basin surrounded by military ranges where access could be tightly controlled. All personnel required top-secret security clearances and special program access authorizations. Even satellite reconnaissance could not reveal the full nature of the program because test flights occurred primarily during hours of darkness or under conditions of heavy cloud cover when satellite passes were not scheduled. Soviet military attachés in the United States filed reports describing unusual sonic booms and atmospheric disturbances over the Nevada desert, but could not determine the source. The first confirmed Soviet awareness of the A-12 came in late 1963, when signals intelligence indicated that Soviet radar tracking stations had detected an aircraft over the Pacific traveling at velocities consistent with Mach 3 flight. The Soviets could not determine the aircraft type, altitude, or mission profile from these fragmentary radar returns. Soviet analysts speculated that the United States had developed an advanced interceptor or that the radar data resulted from equipment malfunction. Not until 1967, when President Lyndon Johnson publicly disclosed the existence of the SR-71 as part of a strategic deception operation to protect the still classified A-12, did Soviet intelligence fully comprehend the magnitude of American technological advancement. Even then, the Soviets believed the SR-71 represented the pinnacle of American capability. The A-12 remained classified until 1982, and specific performance parameters remained secret until the mid-1990s, when comprehensive declassification of CIA documents occurred. The Cuban Missile Crisis of October 1962 drew urgent attention to the Oxcart program. U-2 reconnaissance aircraft had discovered Soviet SS-4 and SS-5 medium-range ballistic missiles on Cuban soil in mid-October, triggering the most dangerous confrontation of the Cold War. U-2's continued overflights to monitor construction progress at missile sites and deployment of nuclear warheads. On October 27, 1962, a U-2 piloted by Major Rudolf Anderson was shot down by a Cuban-operated SA-2 missile. Anderson was killed. The loss demonstrated that U-2 operations over hostile territory equipped with modern Soviet air defense systems were no longer viable. President Kennedy and his advisors urgently needed continued reconnaissance of Cuba, but could not risk additional U-2 losses that might escalate the crisis beyond diplomatic control. The A-12 suddenly had a potential operational mission. CIA officials developed Operation Skylark, a contingency plan to use A aircraft for reconnaissance of Cuba if U-2 flights became impossible. The plan presented enormous risks. In October 1962, no A-12 had yet achieved full operational capability. The J-58 engines continued to experience reliability problems. Maximum demonstrated performance was Mach 2.8 at 78,000 feet, below the design specification and potentially within the engagement envelope of SA-2 missiles. Electronic countermeasures equipment was not yet fully integrated. Nevertheless, the strategic requirement was absolute. In August 1964, after Soviet Premier Khrushchev declared that U-2 flights over Cuba would be shot down after the U.S. elections in November, CIA Director John McCone ordered that Skylark be operationally ready by November 5, 1964. A detachment of 5 pilots and ground crews was organized. Intensive training focused on validating camera performance and qualifying pilots for sustained Mach 2.8 operations over hostile territory. CIA technical officers calculated that Cuban radars would detect the A-12 flights and that SA-2 batteries would attempt intercepts. But they assessed that the combination of altitude, speed, and limited electronic countermeasures would provide sufficient survivability. The Skylark deployment never occurred because political considerations prevented authorization, but the urgency of Cuba preparations accelerated A-12 development and revealed critical technical deficiencies that were subsequently corrected. The first operational deployment of the A-12 occurred under the codename Operation Black Shield in May 1967. 3 A-12 aircraft and support personnel deployed to Kadena Air Base on Okinawa, Japan, to conduct reconnaissance missions over Southeast Asia. The initial mission profile called for photography of North Vietnamese surface-to-air missile sites, airfields, and suspected nuclear facilities being constructed with Soviet and Chinese assistance. The Department of Defense and CIA had grown increasingly concerned that North Vietnam's dense air defense network, consisting of over 200 SA sites integrated with radar-guided anti-aircraft artillery and MiG interceptors, made continued U-2 and RF-4 reconnaissance operations prohibitively dangerous. The A-12 offered the capability to overfly defended areas at speeds and altitudes that rendered interception nearly impossible. On May 31, 1967, pilot Mel Vojvodich flew the first operational Black Shield mission, designated Mission 1001, over North Vietnam. The sortie lasted 3 hours and 41 minutes. The A-12 photographed 70 surface-to-air missile sites, 9 airfields, and numerous suspected logistics facilities in a single pass. North Vietnamese radar operators detected the aircraft and initiated tracking procedures, but the combination of altitude, speed, and radar cross-section characteristics prevented successful engagement. Post-mission analysis of signals intelligence confirmed that multiple SA-2 sites had attempted to lock their fan song guidance radars onto the target, but could not maintain track long enough to compute a firing solution. The A-12 had transited defended airspace and exited before intercept procedures could be completed. On October 28, 1967, pilot Dennis Sullivan flew a Black Shield mission designated 1032 that became the most heavily contested A-12 sortie of the war. Sullivan's flight path took him over Hanoi and Haiphong, the most heavily defended areas in North Vietnam. Signals intelligence equipment aboard the A-12 detected multiple radar systems tracking the aircraft from the moment it crossed into North Vietnamese airspace. On the first pass over the primary target area, Sullivan detected radar tracking, but no missile launches occurred. During the second pass, at least 6 SA-2 missiles were fired from different sites in a coordinated salvo designed to saturate the target area. Sullivan observed 6 missile contrails rising toward his altitude through his rearview periscope, an optical system installed specifically to allow pilots to monitor threats approaching from astern during high-speed cruise when turning the head was impossible. The missiles climbed to approximately 90,000 feet, leaving distinct contrails that were photographed by the A-12's cameras. Sullivan watched as the missiles converged on his flight path. All 6 missiles detonated behind the aircraft as it accelerated through Mach 3.1. One missile exploded within 300 to 700 feet of the aircraft, close enough that Sullivan felt the shock wave as a mild buffet. Post-flight inspection at Kadena revealed that a metal fragment, not a warhead pellet but possibly debris from the missile body or guidance section, had penetrated the lower right wing fillet area and lodged against the support structure of the wing tank. The fragment did not compromise fuel integrity or structural strength. The A-12 had survived the most intensive surface-to-air missile engagement ever directed against a manned reconnaissance aircraft. Soviet missile crews had fired a coordinated salvo using the most advanced guidance systems available, and the target had escaped unscathed. Analysis of mission photography and signals intelligence provided unprecedented documentation of the engagement. Images showed missile smoke rising from launch sites, missile contrails climbing toward the aircraft altitude, and the detonation patterns of proximity-fused warheads exploding in the aircraft's wake. Electronic countermeasures equipment logs confirmed that fan song guidance radars had achieved intermittent track, but could not maintain continuous illumination required for terminal homing. The missile salvos had been fired using estimated target position rather than continuous track, reducing probability of kill to near zero. The speed differential was decisive. An SA-2 missile accelerated to Mach 3.5 but could not sustain that velocity for more than a few seconds. The A-12 maintained Mach 3.2 continuously, meaning that even a perfectly aimed missile would fall behind unless launched from a position directly in the aircraft's flight path, with precise altitude and range prediction. Soviet doctrine assumed that high-altitude targets would maintain straight and level flight during the engagement window, allowing missiles to climb into the target's path and detonate within lethal radius. The A-12 speed meant that even a slight deviation in predicted intercept geometry resulted in the missile detonating hundreds of feet behind the actual aircraft position. North Vietnamese and Soviet analysts studied the engagement data with growing alarm. The radar returns did not match any known aircraft profile. The velocity was consistent with strategic ballistic missiles during re-entry, but the altitude and flight path indicated a manned platform. Soviet engineers analyzed fragments recovered from missile detonations and concluded that the target was an aircraft constructed primarily of titanium with composite materials in critical areas. This revelation triggered intense discussions within Soviet air defense commands. If American reconnaissance aircraft could routinely penetrate defended airspace at Mach 3 and 90,000 feet, the entire strategic architecture of Soviet air defense was obsolete. Surface-to-air missile systems optimized for engaging targets at Mach 2 or below could not reliably intercept platforms with a 200-knot speed advantage and 10,000-foot altitude margin. Soviet interceptor aircraft could not reach the operational envelope where interceptions might be attempted. The MiG-25, the fastest Soviet interceptor, had a maximum speed of Mach 2.83 and a service ceiling of 75,000 feet under ideal conditions. Against a target at 90,000 feet traveling at Mach 3.2, the MiG-25 could not execute a successful zoom climb intercept even if positioned perfectly by ground controllers. Soviet air defense doctrine assumed that altitude sanctuary had been eliminated by the SA-2 and that high-speed targets could be engaged through predictive firing using powerful radars and high-speed missiles. The A-12 demonstrated that a combination of speed, altitude, and modest stealth characteristics could defeat this doctrine entirely. Soviet military journals published after the Vietnam War acknowledged that engagements against high-speed reconnaissance platforms had been unsuccessful and that new missile systems with improved kinematics and guidance would be required. The SA-5 Gammon missile system, introduced in the late 1960s, featured increased range and altitude capability specifically to counter high-altitude threats. The SA-5 had a maximum engagement altitude of 100,000 feet and a maximum speed of Mach 3.5 sustained for longer durations than the SA-2. Whether the SA-5 could successfully engage an A-12 remained an open question because no operational interceptions were attempted. The A-12 program was retired in 1968 before the SA-5 became operationally widespread. The psychological impact on Soviet commanders extended beyond tactical frustration. For years, Soviet propaganda had promoted the narrative that socialist technological development had surpassed decadent Western capitalism. The downing of Francis Gary Powers in 1960 had been celebrated as proof that Soviet engineering could defeat American espionage. The successful satellite interception in 1963 demonstrated anti-satellite capability. The introduction of the MiG-25 was portrayed as establishing air superiority against any potential adversary. The realization that American engineers had developed an aircraft that rendered Soviet air defenses impotent represented a profound humiliation. Worse, the aircraft had been constructed using Soviet titanium purchased through front companies and diverted to military applications. Soviet export controls had failed completely. Soviet intelligence services had failed to detect the program until operational deployment. Soviet air defense systems had failed to intercept a single reconnaissance sortie. The cumulative failure represented a strategic defeat in the intelligence and technological competition that defined Cold War rivalry. Soviet Premier Alexei Kosygin received classified briefings on the A-12 interception failures in late 1967. Documents declassified after the collapse of the Soviet Union reveal that Kosygin demanded immediate acceleration of programs to develop advanced surface-to-air missiles, improved radar systems, and interceptor aircraft capable of Mach 3 sustained performance. The resulting programs consumed enormous resources and produced systems like the MiG-31 Foxhound interceptor, which entered service in 1981 with a maximum speed of Mach 2.83 and look-down shoot-down radar capable of engaging low-altitude cruise missiles. These systems were designed specifically to counter threats like the A-12, but by the time they became operational, the A-12 had been retired for over a decade and replaced by satellite reconnaissance that provided global coverage without risking aircrews. The operational history of the A-12 was brief but consequential. From May 1967 to May 1968, A-12 aircraft flew 29 operational sorties under Operation Black Shield. Missions covered North Vietnam, North Korea, and other denied areas in Southeast Asia. The aircraft photographed military installations, transportation networks, air defense sites, and suspected nuclear facilities with a resolution of 6 inches from 90,000 feet, far superior to satellite imagery available at the time. Not a single sortie resulted in mission abort due to hostile action. Several aircraft sustained minor damage from missile fragments and debris, but all returned safely to base. The cameras aboard the A-12 used specialized film and optics designed by Perkin-Elmer and Eastman Kodak to achieve unprecedented resolution at extreme altitudes. The Type I camera system could photograph a swath 72 miles wide with sufficient detail to identify individual vehicles and weapon systems. Electronic intelligence systems recorded radar emissions, communication signals, and telemetry that provided critical insights into Soviet and Chinese military capabilities. The intelligence collected by Black Shield missions directly supported targeting decisions, assessment of enemy capabilities, and strategic planning throughout the Vietnam War. In June 1968, President Lyndon Johnson ordered the retirement of the A-12 fleet despite its operational success. Several factors drove this decision. The Air Force's SR-71, which had been developed from the A-12 design, was becoming operationally available and offered similar performance with greater range and a two-person crew that reduced pilot workload. Maintaining two separate fleets with overlapping capabilities was financially and logistically inefficient. Satellite reconnaissance systems, particularly the KH-8 Gambit and KH-9 Hexagon programs, were producing imagery with improving resolution and global coverage that did not require overflight of hostile territory. The political sensitivity of manned reconnaissance flights over denied areas had increased after the Powers incident, and policymakers preferred the deniability and reduced diplomatic risk of satellite systems. The final A-12 operational mission was flown on May 8, 1968. The aircraft were flown back to Palmdale, California, placed in secure storage, and eventually transferred to museums after declassification in the 1980s and 1990s. 15 A-12 aircraft were built in total, including two-seat trainer variants. Two were lost in accidents during the test program, both due to mechanical failures rather than hostile action. No A-12 was ever shot down or seriously damaged by enemy fire. The technological legacy of the A-12 extended far beyond its brief operational service. The innovations developed for Oxcart directly influenced subsequent American reconnaissance and strike platforms. The titanium fabrication techniques pioneered by Lockheed became standard for high-performance military aircraft. The SR-71, which remained operational until 1999, used the same basic airframe design, engines, and materials as the A-12. The D-21 reconnaissance drone, designed to be launched from a modified A-12 designated the M-21, demonstrated that supersonic unmanned systems could perform missions too dangerous for manned aircraft. Although the D-21 program suffered technical setbacks and operational disappointments, it established principles that informed later UAV development. The stealth shaping principles incorporated into the A-12 influenced the design of the F-117 Nighthawk stealth fighter and the B-2 Spirit stealth bomber, both of which used faceted surfaces and composite materials to minimize radar cross-section. The concept of using speed and altitude as primary survivability factors, combined with reduced observability as a secondary layer of defense, became a foundational principle in American aerospace doctrine. The intelligence collection methodologies validated by A-12 operations demonstrated that manned reconnaissance platforms could provide timely, high-resolution imagery of strategic targets when satellite coverage was inadequate or when rapid response to emerging threats was required. This understanding influenced the development of tactical reconnaissance variants of fighters like the RF-4 Phantom, and later the integration of reconnaissance pods on multi-role aircraft. If you appreciate discovering Cold War secrets hidden for decades, consider subscribing for future declassified revelations. The story of the A-12 reveals the extraordinary lengths to which American engineers and intelligence officers went to maintain strategic advantage during the most dangerous period of superpower confrontation. The aircraft existed at the intersection of metallurgy, aerodynamics, thermodynamics, propulsion engineering, and operational security in ways that had never been attempted before and have rarely been equaled since. Soviet military literature published after the Cold War provides a remarkable window into the psychological impact of the A-12 and similar American technological achievements. Marshal of Aviation Pavel Kutakov, who commanded Soviet air defense forces during the 1960s and 1970s, wrote in his memoirs that the appearance of Mach 3 reconnaissance aircraft forced a complete reassessment of Soviet defensive capabilities. Kutakov acknowledged that existing missile systems could not reliably engage targets with the speed and altitude performance of the A-12, and that new systems required years of development before deployment. Soviet engineers who defected to the West after the collapse of the Soviet Union provided additional details. Viktor Belenko, a MiG-25 pilot who defected to Japan in 1976, revealed that Soviet pilots were explicitly instructed not to attempt intercepts of high-altitude, high-speed reconnaissance aircraft because the probability of success was negligible, and the risk of losing the interceptor to fuel exhaustion or mechanical failure was high. Soviet doctrine shifted toward accepting that certain American reconnaissance platforms could not be stopped, and that the appropriate response was denial through camouflage, deception, and mobility rather than direct interception. This represented a fundamental change in strategic thinking. For the first time since the introduction of air power in warfare, a defended nation accepted that it could not prevent aerial reconnaissance of its territory. The implications extended to nuclear strategy. If the United States could monitor Soviet missile deployments, submarine construction, and bomber dispersal with impunity, Soviet ability to achieve strategic surprise was severely compromised. This reduction in surprise attack capability contributed to the gradual acceptance of arms control verification provisions that relied on national technical means, including reconnaissance satellites and aircraft, to monitor compliance with treaties. The engineering challenges overcome during the Oxcart program remain instructive for contemporary aerospace development. The titanium fabrication problems encountered by Lockheed engineers illustrate the difficulty of working with materials at the edge of known capabilities. Every aspect of the production process required innovation. Standard welding techniques caused embrittlement. Conventional cutting tools shattered. Chemical contamination from common industrial materials caused structural failures. The solutions required systematic testing, failure analysis, and development of entirely new manufacturing processes. The production line for the A-12 was unlike any previous aircraft assembly operation. Workers wore cotton gloves rather than standard industrial gloves to prevent contamination. Tools were segregated by material compatibility. Water used in cleaning operations was distilled and tested for impurities. Welding was performed in controlled atmosphere chambers to prevent oxidation. Quality control procedures rejected 95% of titanium stock in early production runs because it failed to meet specifications. As manufacturing processes improved, rejection rates declined, but titanium remained an extraordinarily difficult material throughout the program. The development of JP-7 fuel required collaboration between petroleum chemists, engine designers, and materials scientists. The fuel had to remain stable across a temperature range from -60 degrees Fahrenheit at high-altitude cruise to over 300 degrees Fahrenheit in fuel lines adjacent to the engine and afterburner. It had to provide sufficient lubricity to function as hydraulic fluid. It had to burn efficiently in the combustion chamber while remaining too stable to ignite with conventional ignition systems. The final formulation represented a compromise among competing requirements, and the addition of cesium compounds for signature reduction created handling challenges because cesium is highly reactive and toxic. Ground crews handling JP-7 required specialized training and protective equipment. The fuel was so stable that workers could extinguish matches by dipping them into JP-7, a demonstration frequently performed to illustrate the safety characteristics, but one that also highlighted the ignition challenges that required trithylboring cartridges for engine start. The radar cross-section reduction achieved by the A-12 was modest by modern stealth standards, but represented cutting-edge technology in the early 1960s. The chine design and composite leading edges reduced frontal radar cross-section by a factor of 3 to 5 compared to conventional aircraft, depending on frequency and aspect angle. This reduction translated directly to decreased detection range and increased warning time for defensive maneuvers. Soviet P-12 and P-14 radars operating in the VHF and UHF bands could detect the A-12 at ranges of 60 to 80 miles, instead of the 100 to 120 miles typical for conventional aircraft. This gave A-12 pilots an additional 2 to 3 minutes of warning before entering the engagement zone of SA-2 missiles, time that could be used to adjust flight path, activate electronic countermeasures, or abort the mission if threat levels exceeded acceptable parameters. The composite materials used in radar-absorbing structures consisted of iron ferrite particles suspended in a honeycomb matrix. The iron ferrite absorbed electromagnetic energy and converted it to heat, which dissipated through the surrounding structure. The effectiveness of these materials varied with radar frequency. VHF radars, which had long wavelengths, were less affected by the small-scale structures of the composites. X-band radars, operating at higher frequencies with shorter wavelengths, showed greater attenuation. The A-12's stealth characteristics were optimized primarily against X-band fire control radars like the Fan Song system used to guide SA-2 missiles. By reducing the effective range at which Fan Song could achieve and maintain lock, the A-12's designers increased the geometric requirements for successful interception to the point where missile kinematics became the limiting factor rather than radar detection. The operational procedures for A-12 missions reflected the extreme performance envelope and strategic sensitivity of the aircraft. Missions began with extensive pre-flight planning conducted by CIA operations officers, photo interpreters, and mission planners. Target areas were selected based on intelligence requirements developed by the National Security Council and Department of Defense. Flight routes were calculated to minimize exposure to known air defense sites while ensuring camera coverage of high-priority targets. Weather forecasts were critical because cloud cover could obscure targets and render photography useless. Pilots received detailed briefings on expected threats, including locations of radar sites, surface-to-air missile batteries, and interceptor bases. Electronic countermeasures settings were programmed based on the specific radar frequencies known to operate along the flight path. Pilots donned full-pressure suits, which required assistance from specialized technicians. The suit pressurization system was tested to ensure integrity because failure at 90,000 feet would result in rapid decompression and death within seconds. The pre-breathing protocol required pilots to breathe 100% oxygen for at least 30 minutes before flight to purge nitrogen from the bloodstream and prevent decompression sickness. Engine start required ground support equipment to provide electrical power and pneumatic pressure because the onboard systems could not initiate the start sequence independently. Once engines were running, pilots performed system checks of navigation equipment, cameras, electronic countermeasures, and flight controls. Takeoff was performed with partial fuel load because the A-12 could not become airborne at maximum gross weight. Immediately after departure, the aircraft rendezvoused with a KC-135Q tanker for aerial refueling to full fuel capacity. The refueling was conducted at subsonic speed and moderate altitude, typically 25,000 to 30,000 feet. After refueling, the pilot climbed to operational altitude and accelerated to cruise speed. The acceleration and climb to Mach 3 and 90,000 feet required approximately 20 minutes and consumed a significant portion of fuel. Once at cruise, the aircraft maintained speed and altitude with minimal control inputs. The autopilot system handled most navigation and attitude control. The pilot monitored systems, operated cameras at designated waypoints, and maintained awareness of threats through radar warning receivers and electronic intelligence systems. The cameras were activated automatically by the navigation system at pre-programmed coordinates, ensuring precise alignment between ground features and film exposure. Over hostile territory, pilots maintained radio silence unless emergency communication was required. Navigation relied on inertial navigation systems that used gyroscopes and accelerometers to track position based on dead reckoning from known starting coordinates. The accuracy of inertial navigation degraded over time due to cumulative errors, but missions were short enough that positional uncertainty remained within acceptable limits. After exiting hostile airspace, pilots descended to refueling altitude for a second rendezvous with tankers. The return flight to base was flown at subsonic cruise to conserve fuel. Landing approach was conducted at high speed because the A-12's aerodynamic design provided minimal lift at low speeds. Touchdown speed exceeded 200 knots, requiring precise control and a long runway. After landing, film canisters were immediately removed from the aircraft and transported to processing facilities where specialists developed the film and produced prints for analysis. Photo interpreters examined the imagery for military installations, equipment, and activity indicators. The entire process from landing to initial intelligence assessment required less than 12 hours, providing near real-time strategic reconnaissance. The political decision to retire the A-12 in favor of the SR-71 and satellite systems reflected changing strategic priorities and technological evolution. By 1968, satellite reconnaissance had matured to the point where regular coverage of the Soviet Union, China, and other denied areas was routine. The KH-8 Gambit satellite, which became operational in 1966, provided imagery with resolution comparable to the A-12's cameras, though from much higher altitudes and with less flexible targeting. The KH-9 Hexagon, operational from 1971, could photograph vast areas with sufficient resolution to detect military installations and assess large-scale deployments. Satellites offered several advantages over manned aircraft. They could not be shot down by surface-to-air missiles or interceptors. They did not require overflight permissions or create diplomatic incidents. They provided global coverage on predictable schedules. However, satellites also had significant limitations. Orbital mechanics dictated when satellites would pass over specific targets, reducing responsiveness to emerging crises. Cloud cover could obscure targets for days or weeks. Resolution, while improving, remained inferior to low-altitude photography for detailed analysis of small objects. The complementary nature of satellite and aircraft reconnaissance was well understood by intelligence planners, but budgetary and political factors favored satellite investment because of reduced risk and greater strategic stability. The SR-71, operated by the U.S. Air Force rather than the CIA, provided an overt reconnaissance capability that could be acknowledged publicly without revealing sensitive technical details or operational procedures. The two-person crew of the SR-71 distributed workload between pilot and reconnaissance systems officer, reducing fatigue and improving mission effectiveness on long-duration flights. The SR-71's greater fuel capacity extended range to over 3,000 miles unrefueled, enabling missions that required fewer aerial refuelings and reduced dependency on tanker support. The decision to maintain the SR-71 fleet while retiring the A-12 represented a rational allocation of resources given these operational considerations. The broader strategic context of the A-12 program reveals the intensity of Cold War technological competition. The United States and Soviet Union devoted enormous resources to developing systems that could provide decisive advantages in intelligence collection, strategic deterrence, and tactical operations. The A-12 represented one element of a comprehensive American strategy to maintain information dominance through multiple overlapping capabilities. Satellites provided global area coverage. U-2 aircraft offered high-resolution imagery of permissive or semi-permissive environments. The A-12 and later SR-71 filled the niche of high-resolution reconnaissance over heavily defended areas where satellites could not provide sufficient detail and U-2s could not survive. Electronic intelligence systems aboard ships, aircraft, and ground stations monitored Soviet communications and radar missions. Human intelligence sources provided context and intent that technical systems could not determine. The integration of these capabilities created an intelligence architecture that allowed American policymakers and military commanders to understand Soviet capabilities, deployments, and intentions with unprecedented fidelity. This information advantage influenced strategic decisions during crises like the Cuban Missile Crisis, arms control negotiations, and assessments of the military balance. Soviet leaders understood that American reconnaissance capabilities constrained their options for surprise attack or covert deployments. This understanding contributed to the development of arms control agreements that incorporated verification provisions based on national technical means. The phrase national technical means became diplomatic code for reconnaissance satellites and aircraft, and the acceptance of this phrase in treaty language represented Soviet acknowledgement that American intelligence capabilities could not be defeated, and that transparency might serve mutual interests in reducing the risk of accidental war or miscalculation. The pilots who flew the A-12 constituted an elite cadre selected for exceptional skill, judgment, and reliability. The CIA recruited pilots with extensive military experience, typically former Air Force fighter or reconnaissance pilots with spotless records and top-secret security clearances. The selection process included psychological evaluations to assess stress tolerance and decision-making under pressure. Physical examinations verified that candidates could withstand the extreme physiological demands of high-altitude, high-speed flight. Training began with classroom instruction on the aircraft systems, performance characteristics, and emergency procedures. Pilots studied aerodynamics, propulsion, navigation, sensors, and survival equipment. Simulator training allowed practice of normal and emergency procedures without risking the aircraft. Initial flights were conducted with chase planes and extensive ground monitoring. Pilots progressively expanded the performance envelope under controlled conditions, building experience and confidence. The first solo flight in the A-12 was a significant milestone because the aircraft's performance was so extreme that mistakes could be fatal. Several pilots died during the test program in accidents caused by mechanical failures, pilot error, or the inherent risks of experimental flight. Jack Weeks, one of the most experienced A-12 pilots, flew numerous operational missions over North Vietnam and North Korea. His accounts of these missions, declassified decades later, reveal the tension of penetrating hostile airspace while being tracked by multiple radar systems and knowing that missile launches could occur at any moment. Ken Collins survived an A-12 crash in 1963 when a flight control malfunction caused the aircraft to pitch uncontrollably during a high-speed test flight. Collins ejected successfully and landed safely, but the aircraft was destroyed on impact. The crash site was immediately secured by military personnel and the wreckage removed before civilian observers could arrive. The cover story released to the public described the incident as involving a classified research aircraft but provided no details. These pilots understood that their missions directly supported national security but received no public recognition during their operational careers because the program was classified. Not until the 1990s, when the A-12 program was fully declassified and details released to the public, did their contributions become known outside classified circles. The final accounting of the A-12 program reveals a paradox common in Cold War intelligence operations. The aircraft was extraordinarily successful in meeting its design specifications and operational requirements, but flew relatively few missions before retirement. The total operational deployment lasted 13 months and produced 29 combat sorties. This limited operational use might suggest inefficiency or poor planning, but the strategic impact extended far beyond sortie count. The existence of the A-12, even when its details remained classified, signaled to Soviet leadership that American technological capabilities exceeded Soviet assessments, and that attempts to create sanctuary through air defense systems would fail against determined American reconnaissance efforts. The intelligence collected by A-12 missions informed critical decisions about Vietnam War strategy, assessments of North Korean nuclear activities, and evaluations of Chinese military developments. The technological innovations pioneered by the program influenced American aerospace development for decades. The psychological impact on Soviet military planners contributed to shifts in doctrine and resource allocation that affected the broader strategic competition. The A-12 demonstrated that speed, altitude, and modest stealth could defeat even sophisticated integrated air defense systems, a lesson that informed American development of the F-117, B-2, and later stealth platforms. The program validated the concept that technological superiority could provide decisive advantages in intelligence collection and strategic operations, even against adversaries with numerical superiority and home field advantage. Soviet reactions to American technological achievements like the A-12 followed a consistent pattern throughout the Cold War. Initial denial and dismissal of reports gave way to grudging acknowledgement when evidence became overwhelming. Acknowledgement triggered crash programs to develop countermeasures or equivalent capabilities. These programs consumed resources, diverted talent from other priorities, and often produced systems that arrived too late to counter the original threat but contributed to ongoing technological evolution. The Soviet response to the A-12 and SR-71 included development of advanced surface-to-air missiles, improved radar systems, and faster interceptors. The SA-5 Gammon missile system, introduced in 1967, featured longer range and higher altitude capabilities specifically to engage Mach 3 targets. The SA-10 Grumble, operational in 1980, incorporated advanced guidance and propulsion to engage low-altitude cruise missiles and high-altitude reconnaissance aircraft. The MiG-31 Foxhound interceptor, operational in 1981, combined Mach 2.8 speed with look-down shoot-down radar and long-range missiles designed to intercept cruise missiles and reconnaissance aircraft at extended ranges. These systems represented significant technical achievements, but arrived years after the threats they were designed to counter had evolved or been replaced. This temporal mismatch characterized much of Soviet technological response during the Cold War. American innovation cycles were shorter, secrecy was more effective, and integration of new capabilities into operational systems occurred more rapidly than Soviet responses could match. The cumulative effect was a persistent American advantage in reconnaissance, strategic mobility, and precision strike capabilities that influenced every major Cold War confrontation, and contributed to the eventual collapse of the Soviet Union when economic resources could no longer sustain military competition. Join us here at Classified Warfare as we uncover the operations and technologies that kept the world on the brink. The story of the A-12 Oxcart reveals a fundamental truth about strategic competition in the modern era. Information dominance determines outcomes before the first shot is fired. When one side can see the battlefield with clarity while the adversary operates in uncertainty, tactical and operational advantages follow inevitably. The United States invested enormous resources in developing capabilities like the A-12 precisely, because American strategists understood that knowledge of enemy capabilities, deployments, and intentions would allow efficient allocation of defensive resources, effective deterrence through demonstrated awareness, and decisive action if conflict became unavoidable. The Soviet Union, despite matching or exceeding American military forces in many quantitative measures, never achieved comparable intelligence collection capabilities. Soviet satellites were less capable, Soviet reconnaissance aircraft were more vulnerable, and Soviet human intelligence networks, while extensive, could not compensate for technical collection deficiencies. This information asymmetry influenced every major decision point of the Cold War, from the Cuban Missile Crisis through arms control negotiations to the final collapse of Soviet power. The A-12 was a single element of this larger strategic architecture, but it embodied the principles that guided American Cold War strategy: Technological innovation, operational security, integration of capabilities across multiple domains, and willingness to accept risk in pursuit of decisive advantage. The aircraft flew faster than Soviet missiles could track, higher than Soviet interceptors could climb, and carried sensors that could photograph installations Soviet leaders believed were hidden from observation. In doing so, it demonstrated that American engineering could turn Soviet confidence into strategic miscalculation and transform titanium purchased from Siberian mines into the instrument of Soviet humiliation. The legacy of that achievement extends to the present day in reconnaissance platforms, stealth designs, and the enduring principle that those who see first and understand most clearly will prevail in the competitions that shape the international order.